So let's look at review Fourier transforms quickly, because that's going to be useful to address power spectrum for stationary stochastic processes also. If you recall, Fourier transform is minus infinity to plus infinity ft e raised to minus j omega t dt, right? And the equally important is the inverse Fourier transform. So you generally remember this is in time, this f omega is in frequency. Because f omega can be complex, you really have to plot the magnitude and phase separately, but generally the magnitude is what is plotted, but phase is equally important. So let's say, so you can see here most of the energy is concentrated around the baseband, so we call this a low pass signal. This is a low pass signal the way I have drawn, right? And the inverse Fourier transform relation is 1 over 2 pi f omega e raised to plus j omega t d omega. This is not dt. Here we are integrating with respect to time to produce a frequency. So the notation is, we will use this notation. So maybe a few things are interesting. What is the Fourier transform of f of minus t? What is the Fourier transform of f star of t? What is the Fourier transform of f star of minus t? What if I bring this shape into the time domain, right? What's the Fourier transform here? And what is the Fourier transform of delta t? What if I modulate a signal with, remember this is being modulation, right? Amplitude modulation. What is the Fourier transform? And what if I convolve with two signals? What if I do this? What if I do that, right? So this we can, let me see, maybe quickly I will do some of this. And this will be useful to you. Also, what is the transform of this? This is generally important. So if this is a pulse of, let's say, width t, so width is t, and let's say height t is 1 over t. So what is its transform? Okay. So let's see whether we can answer some of this. So easiest thing is just to do it. So what is the Fourier transform of f of minus t? It will be f of minus t e raised to minus j omega t dt, right? Then you change, I'll do it here. So change, let me put a new variable. Instead of minus t, I put u. Think of that as u. So this minus t will become plus, and this will become minus dt. But the limits will become plus infinity to minus infinity. This is the expression you get. But this you can see is what? F of? Right. So you got the answer. So the Fourier transform of this is f of minus omega. So if it is star here, this is f star of t e raised to minus j omega t dt. So I can pull out the star outside, right? Then this will become plus, right? So what is the inside quantity? Anybody with a plus here? So that's, look at here. If I put minus here, this will become plus, right? So that's f of minus omega. So this is f of minus omega star, right? And similarly, this is what? This is integral f star of minus t e raised to minus j omega t dt. So first of all, I pull the star outside, so that goes here. This becomes plus. Then we go through, I change minus t to a new variable. So this will become like this, right? So what is it? Right. So you just do it like that. So this is f omega star, right? All right, this is interesting. So I'm going to do this for you somewhere here. So look here, I can do it here itself. This t and this t are the same. So I can replace it by some other variable, right? So I can rewrite this expression as fu equals 1 over 2 pi minus infinity to plus infinity capital F of omega e raised to j omega u du, d omega, right? Now this is a dummy variable here. So I can replace it by something else, right? So that's also fine, right? And then I change my mind again. So I'm going to replace this again by something else. I'm going to replace this by omega now. Then you see, wherever I had u here, I should replace it by what? Omega, right? So in order not to confuse you, I'll write one more line. So let me write the other line. So I have f of u equals minus infinity plus infinity fv, right? E raised to j v u dv, right? Now I am going to replace u with something else. I feel like doing it with omega here. So I have f of omega, small f of omega is 1 over 2 pi minus infinity plus infinity f of v e raised to j omega v dv. Okay? Look at v. V has no meaning. It's a dummy variable. So I'm going to change it by t. So this I get 1 over f of t minus infinity plus infinity f of t e raised to j omega t dt, right? Then I'm going to bring this 2 pi here, and I feel like changing omega to minus omega. So look at the right side. But what is the right side? Fourier transform of? This is what we wanted. We wanted the Fourier transform of f of t, capital F of t. So this is an important identity. So if you do the Fourier transform and you get some shape, if you want to bring this shape into the time domain, you may say, why am I doing all this? You will see it's very useful. So the answer it is 2 pi of f of minus omega. There is a minus here, okay? And this, you know, the answer is 1, right? So if you bring the shape into the time domain, what happens? Look at here. Delta t, the transform is 1, right? Anybody knows why? Because it is delta t multiplied by e raised to minus j omega t dt. By definition of delta t, this is 1, right? When t equal to 0, this is 1. So that's the answer, right? Area under the delta t. So what if I bring this 1 into the time domain? Anybody? So look, delta t has a transform of 1. Ft has a transform of f omega. If I bring the shape into the time domain, what will be the transform of 1? Anyone? Delta of minus omega, but delta is a symmetric function. So this will be useful. And this, of course, you can plug it in here. You see, where is it? So if this is ft e raised to j omega t, this will be omega minus omega naught, right? So you should be able to see that this is f of omega minus omega 0, etc. So let's do the last one. And this will be, so ft convolved with gt will be minus, in general, this is the convolution. Anyway, convolution is what? F tau g of t minus tau d tau. So let's do the Fourier transform of this. So let me call this to be r of t, right? Or s of t. So s of omega is, I should do the Fourier transform, right? Of ft convolved with or st e raised to minus j omega t dt But for st, I'm going to substitute this expression. So that's minus infinity to plus infinity, minus infinity to plus infinity, f tau g of t minus tau e raised to minus j omega t dt d tau, right, d tau. So of course I can rewrite this as so one integral on tau, the other integral is on t minus tau. Look, I introduced minus j omega tau, but there is a plus j omega tau, so it goes away. So you are back with one term, but this is on t minus tau. So if I define a new variable u, this will be u, this will be u. So you see two different variables. This is dealing with tau, this is dealing with u. What is this quantity? Anybody? That's the Fourier transform of f. And what is this? This you can read it as gt e raised to minus j omega t dt. What is that? Alright, so this is a classic result. If you convolve two functions in time, the Fourier transform is the product. So what will happen if you convolve ft with h star of minus t? Anybody? What is the Fourier transform? So Fourier transform of the product, right? So Fourier transform of the first one. What is the Fourier transform of the second one from that list? H star of minus t. Huh? Just a H conjugate of omega, right? So you don't have to start all over if you know the properties. Okay. And so on. Or maybe one more thing here. So what is the Fourier transform of this pulse? It's a very useful stuff. Remember, this is in time domain. So let me call this ft. I put the height to be 1 over t. Fourier transform is what? Look at here. Minus infinity to plus infinity, but the pulse only lives from minus t by 2. So lower limit is minus t by 2 to t by 2. The pulse value is 1 over t, e raised to minus j omega t dt. So 1 over t goes outside. The integral is what? E raised to minus j omega t over minus j omega minus t by 2 to t by 2. So upper limit minus lower limit is what? Anybody? No? What did you say? Yeah, that's minus 2 sine omega t by 2, right? So yeah, so this you get 2j sine omega t by 2, right? Over omega t, right? Minus minus cancels. I'm going to bring this t over here, and there is a j cancel. There is a minus that also cancels, right? So you see omega t. So this is sinc sin x over x, right? So the answer is sinc omega t by 2. So let me draw a picture here. So if I want to sinc omega, what would be the pulse here in time domain? Anybody? I want the t by 2 to be what? T by t to be 2, right? So this is from minus 1 to 1, and this is 1 by 2, right? So t is 2. Right, so let me call this f of t or f naught of t. So what will be the, look at here, this is a new problem. What will be the transform of sinc t? Anybody? That's all over. You can't do it by, you cannot plug this into expression and start doing it. You have to use properties. Which property will you use? So if ft has a transform of capital of omega, then what? We look at here. We want to bring this shape into the time domain. Remember, sinc omega, of course, looks like this, right? This is sinc omega. So what is the transform of sinc t? Looks like this, right?
Minus 2 pi.
Why minus? ft, look at here. So if ft, if this is, I'm sorry, if this is, so this is f naught of t, then this is f naught of omega, then we want f naught of t. So what is the transform of f of t, capital F of t? So what will it look like? Anybody? 2 pi multiplied by, this is your small ft, right? So what, 2 pi multiplied by this, right? In the frequency domain. So what will be the lower limit here? Anybody? Might not, this is an omega domain, but this will be the transform. So look, a pulse, you know this, a pulse transform is low pass because most of the energy is concentrated. Transform of a pulse is sinc omega, but sinc t transform is a pulse in the frequency domain. This is frequency, this is time. So if you, if I know the transform of ft, what is the transform of f squared t? Anybody? Small f squared t.
Convolution of f on f and x.
Yeah, you can go from there here also, right? If you convolve, look at here, if you convolve ft with ft, what happens? We just did it here, right? If you convolve ft with ft, f omega squared. If ft is convolved with f star of minus t, yeah. So what is the transform of this? If ft is convolved with f star of minus t, what do you get? All right, so you should be able to see this, right? Right? And the multiplication, you can see the duality also works. If you multiply a function, it is going to be convolution in this domain. Now, so what happens if you convolve a pulse with a pulse in the time domain? If you convolve a pulse with a pulse, what do you get? Huh? A pulse, that pulse with itself, what do you get? Hello, this pulse is convolved with itself. This pulse in the time domain, I'm not going to frequency domain.
It's the shape is like a triangle.
All right, so you get a triangle. So if a pulse is convolved with a pulse, you get a triangle, right? Or if this is from minus t by t to t by 2, what is this from?
Minus t to minus 2.
Okay, wonderful. And what's the height? 1 over t multiplied by 2t. So it is multiplied by t. See, what is, remember, the function multiplied by the other one. I think it is 1 over t. That's what I think. So what is its transform of a triangle? Remember, I convolved the two pulses. So the transform is going to be square. So this is going to be sinc squared t, right? I mean sinc squared omega t by 2. Etc. So you can start so its inverse transform is going to be a triangle in the frequency domain and so on, right? So let's just finish it up by looking at this problem. Look at here. Let's apply these things. If it is a Whiteson stationary process, you have an autocorrelation function Rxx tau, right? And it has its own power spectrum, which is minus infinity to plus infinity Rxx omega, Rxx tau e raised to minus j omega tau d tau. We know the power spectrum is positive, so let's say it's something like this. Now you have, we have learned all this, right? You have the cross correlation function between x of t and y of t is given by what? Few weeks back we learned, right? No?
Convolution is
Rxx tau convolved with?
h tau minus.
Right. So remember, y of t is of course x of t convolved with h of t. We went through all this, right? This is, so the cross correlation function is Whiteson stationary. X of t and y of t are jointly Whiteson stationary. And ryy tau was what? Anybody? H of tau, right? So from here you can find out the cross spectrum. So if I take the Fourier transform of this, we will call it the cross spectrum. So what is the cross spectrum? Remember there is a convolution here. So you get Sxy omega is what? The Fourier transform of this?
Multiplied by
Fourier transform of this. What is the Fourier transform of this?
h tau.
So this is Sxx omega multiplied by just h star of omega. We have it there, right? And look at here. And the output power spectrum is what? This is convolution here, right? So this is the power spectrum of this multiplied by the transform of h of tau. So that's going to be Sxy omega multiplied by h omega. Let me substitute here this one. So you get Sxx omega multiplied by h omega absolute value squared. So that's the important expression. I'll write it here. So output power spectrum is input power spectrum multiplied by the system transfer function squared, right? So look, the output power spectrum is input power spectrum multiplied by system transfer. This gives us ideas how to design. We can use this to do receiver design. Look at here. So if you know that the Sxx omega has got all this shape, but you are interested to know whether there is something around omega naught, what should be the shape of h of omega? If you only want to retain, suppose this is the band you are interested in. Okay. Look at what it says here. So if you pass the process through a filter, you can shape the frequency characteristics of this. Because this is the relation, the output shape is input shape multiplied by the filter. So if you only want to retain there, I should use a filter like this, right? It's a band pass filter. And of course we know or for example, if you wanted to retain here, you will use a low pass filter, etc. So look at here, if the output is maybe we have been using this term white noise. So if the spectrum happens to be flat, if the spectrum of any process is flat, then it is like the sunlight, right? Sunlight has got at least all the visible frequencies equally represented. So that's so it's white light. It's like white light. So we call this white noise. So like a delta function, this is an idealization because this is not realizable. What is the reason? What is the total power under this process? Anybody? So that infinity, so that doesn't make, so it's an idealization. Really what we mean generally is that whatever is your frequency band, let's say you say I'm going to operate from minus or 100 gigahertz. So over 100 gigahertz you want flat frequency. That's what we mean. So this is white noise. A more realistic is this one. Over certain frequencies, so this we call it colored noise. So what is the autocorrelation function of a colored noise? First of all, what is the autocorrelation function of white noise process? Anybody? If the spectrum is flat, I am asking if the spectrum is flat, what is the autocorrelation function? Delta function, right? Very good. Look at the properties, it's right there in front of you. So what is the autocorrelation function of colored noise? We have done it. Spectrum is like this in the, so what is it? Okay, tell me the values exactly. Alright, so you can get it for, see, put in that, look at there. You put in that expression omega, I mean t by 2 equal to beta, right? Or you just do the inverse operation, right? So let's do the inverse operation. So this is minus b naught to b naught. It will come out to be Sinc, you are right. So this is 1 e raised to j omega or tau d omega. So this will come out to be 2j sine b naught tau over a tau, right? J tau, right? So it's b naught over pi Sinc b naught tau, right? So in the time domain, the autocorrelation function is going to look like this. So where is this first zero? Anybody? Where is this zero? Sinc b naught is what? Look here. This is sine b naught tau over b naught tau. Did I miss a 2 here? No, that's good. So when this quantity sine pi by 2 is 1 or 0? Sine pi by 2 is 1. You should be going back to elementary classes. Sine pi is 0. So this is corresponds to pi, the b naught tau equal to pi, right? Or this tau 1 is equal to pi over b naught, right? 1 over bandwidth. So this is an interesting problem. Suppose you listen to this now. Suppose you pass a white noise process, a white Gaussian noise process. So W of t is white and Gaussian. This is a linear filter. So the output will be what? If you put in Gaussian, what happens to the output? Also Gaussian, right? So this is a colored Gaussian, right? The power spectrum will look like this, right? Because this power spectrum is like this. This is the power spectrum. This is, so this is RNN. This is the autocorrelation function of the output. So if you have this process n of t, N of t is, let's say this is one realization. Suppose I take some time instant t1 here, and I take another time instant t1 plus tau1. What will be the correlation between these two samples? Anybody? Look, I take a sample nt1 and I take another sample nt2. But the t1 minus t2 is, let's say I adjust it to this distance, so tau1. So what will be the correlation between these two random variables? Huh? Rnn of tau minus tau, right? But Rnn is symmetric. Anyway, Rnn is minus tau is here. So what is the value? Look at the picture. Why are you so shy? You can shout 0, right? Right? So two Gaussian random variables are what? Remember, let's assume it is 0 mean. So you have expected value of nt1 multiplied by nt2 to equal to. So two random variables are what? But they are Gaussian. So they are also independent. So you can deduce all this stuff. So let me summarize what I said. See whether it makes sense. If I pass a white Gaussian noise process through a low pass filter, I can, by adjusting the bandwidth, I can make the output samples at a particular time periodically independent. You have to put everything together, 2 plus 2 plus 2 plus 2 plus 2, etc. So white Gaussian will generate a Gaussian process which autocorrelation is Sinc function. Sinc function goes through 0 periodically. So if you sample this process at sampling time equal to tau1, what happens to all those samples? They're all independent. So that's one way if you want to. But of course, if you take any other sampling time, the process is not independent. So see whether you can prove this. Of course, I have proved it. You take a Gaussian process, but white noise. You pass through a low pass filter with the bandwidth B0. It's a Gaussian process. Then you sample that output. Sampling time is this tau1. Do you see that all the samples are independent? Of course, you should see it because we just went over the results. All right, next I'm going to do match filter. But so that's another application of this.